Good afternoon, everybody. So we'll start with our third lecture, that is on introduction to coal preparation. So what I will do, we have to know what is coal and then why do we need to prepare it, prepare for whom and how. So briefly I will try to introduce that within 1 hour time. So what is coal? Coal is basically a rock, but many times there is our mining professor, they say it is not even a rock, it's an agglomerate. Okay, basically rock consists of organic and inorganic mineral materials. So why we have got a special lecture, as isolated lecture on coal preparation, when I have already introduced mineral processing. So mineral, if you remember, the definition was inorganic, naturally occurring material. This is also naturally occurring, but this is not inorganic. It is a mixture of inorganic and organic compound. So by textbook definition, coal is not a mineral, but for your industry applications, for mining point of view, we say that we treat coal along with the minerals also. So from textbook difference, say actually textbook point of view, by definition coal is not a mineral. So we have got macerates, means organic and mineral matters. Now where from the macerates are coming? If you look at the formation, it is basically, we call it fossil fuel created from the remains of plants that lived and died about 100 to 400 million years ago, even before the dinosaurs age. Okay. It is a non-renewable energy source because it takes millions of years to form. So we have to be very careful when you are using coal, which we are not in most of the cases. Okay. So a day will come when you will not have coal for your use. And the coal seams, that is, when the formation is there is a thickness of the layers. That is, if I have coal component, what is the thickness of my layer? We call it seam, or actually basically it's a bandwidth type of thing, we call it seams. So it may range from a fraction of an inch, very thin, to hundreds of feet. So thicker the coal seam, better the quality of mined coal. Thinner, because on top and bottom there will be some unwanted material. So when you are mining, there will be more contamination. Okay. Now coal composition, if you look at, it is basically a complex mixture of carbon, you can have metal compounds, several other compounds such as hydrocarbons, organic sulfur compounds, hydrogen sulfide, ammonia, water, complex molecules such as stars, which are released, some being burned during combustion of the coal. When you burn a coal, you find that some red flame is going out immediately, that is, we call it volatile matters, that is nothing but the tars and hydrocarbons. Okay. And its composition varies widely according to location. We cannot guarantee, even that is true for minerals, that whatever I am digging here and I am digging here, if whatever material I am getting, I cannot guarantee that they are identical because they are nearby, they are neighbors. No, we cannot give guarantee. So that is the problem with the naturally occurring minerals and coals. Okay. Now why we have all sorts of things, and you have seen that the list goes on. We cannot give specifically write that in coal we have this. Why? So for that we have to look at how the coal was formed. We have to understand a bit of that. So our coal, we call it drift origin. Drift origin means, that is what is saying that millions of years ago, all these trees and big plants and everything, they were basically swamped, they were carried to some distance, and they were buried into the land under the dirt, and then there will be debris, there will be any particle which you don't have control, and they are getting intermixed, and then after that you have a huge heat and pressure, and your for a prolonged duration of time, it could be millions and millions of years. So, if you look at that is a time, pressure and heat, and then it is deposited like this example I gave, do not take it otherwise, that is a suppose if something happens today like tsunami or something, and this entire thing along with us we are buried. So, what will happen? You are having some wooden material, we are also having carbons, and there are basically concretes and all this, and say suppose you imagine after 100 millions of years it gets converted into coal. So, can you guarantee that what is the composition? And next door also happens same thing. So, we do not know what you are carrying, how much of metals are there, what type of materials are there into this room, that could be different. So, that is the problem with our drift origin coal, that the nature of impurities are different, they vary from place to place. Okay? That is the problem with our coal. Now, depending upon this, that is what is the time duration, what is the pressure and what is the temperature. So, the maturity, we call it the maturity of the coal. So, what will happen? Suppose, and then we have got water in this, we are all basically under heat and pressure for a prolonged duration. So, more heat and more pressure means the water content will be less, it will be more compact. So, the more compact, less water means more concentration of carbon rich materials, less dilution. So, that analogy if you look at, so the pit, it is basically the relatively younger one, that means it has undergone maybe the similar amount of pressure and heat, but the time duration could be less. So, it is very soft type of coal, we do not call them coal, we call it peat, because we have got very high moisture content, it is having different properties, okay. Does not have much of heating value into that, because the heating value, the energy whatever is you are getting from a fossil fuel, that is coming from your carbon rich part. Okay. So, then as the process goes on with time, that is called, we call it lignite, we call it even the brown coal. We have got lignite corporation, that is a naval lignite corporation. Then the coal stage comes, even for coal also we have got different basically the nomenclatures. So, if you look at the coal formation, so it comes from dead plant matter falling into the swampy water under heat and pressure, this material goes into decomposition and you get this. So, 4 stages in coal formation I have already discussed, peat, lignite, and then in coal also you can have 2 varieties, normally we call it bituminous and anthracite. Anthracite is the hardest one and the purest one, okay, because it is more matured coal we call it. The stage depends upon the conditions to which the plant remains subjected after they are buried. So, it depends on the process conditions, how much of heat, how much of temperature, but it is very difficult to measure them. So, we characterize based on the characteristics of the material carbon rich part we get, and we call them that this is peat, this is lignite, this is this coal, this is that coal, like that we grade them. Now, if you look at that is your in the coal, if I look at it under microscope, even the maceral part they can have different say type of reflectivities, you know. There are many, the which part of that tree that is getting converted into coal, that also decides what will be the quality of my carbon rich part, basically the reflectance and all this. Okay. So, we call it vitrine, clarine, fusion, like that. There are different names the geologists have given. So, this is basically you look at when we call it the petrographic composition of coal. So, you look at that what type of phases are there, vitinites, inertinites, liptinites, then we have got ash. Ash is not a basically composition of coal. Many people have got this misconception that coal is composed of carbon and ash. S is basically an indirect measure of knowing how much of inorganic material is there. That is also approximate. Okay. So, S is nothing but after burning the coal, once you have ensured that all your carbons and volatile matters have gone out of the system, what you are remaining with, that is your S. That may not be 100% mineral matter, you may not get, but say suppose I say 40% S, but suppose if I have calcium carbonate with my coal, so when I am heating the coal, the calcium carbonate can be dissociated with CO plus CO2, so CO2 may go out, so my percentage could be different, but we get an guesstimate or rough estimate of the mineral matter contained in that coal. That is why we take S, because it is very simple to measure, it is very simple to determine what is the S contained of that coal. So, these are the different colors you may have, that is anthracite, more glazy material, more dark material. Then you have got bituminous. Bituminous can be again having two different categories, subbituminous, bituminous varieties. Then next stage, ultimate stage is graphite, and next stage diamond. So, diamond is also carbon, graphite is also carbon, these are also carbon. So, it depends on what type of pressure, what type of heat, what type of conditions it has undergone. So, why we have to worry about the coal? So, what are the basically the coal quality means? Because mineral processing, as I said, that the mined product I have to convert it to a level of quality which is acceptable by my client. So, where the coal is being used, what are the major applications for coal? I will give you all these PPT slides, okay? No problem. So, do not worry. Okay. So, in the coal major utilization, if you look at the broad application can be divided into two, but there are many other applications. One is for generating energy. So, that is your power generation. Okay. Another one is for making steel. Metallurgists, can you guess where it is required? The coal, for I say that for metallurgical uses it is required. So, that coal we charge when we reduce the iron oxide to iron in blast furnace, we need coal. Coal is having there the two roles to play. One is as a reducing agent, another one is to supply the heat. So, it plays dual role, but there I cannot charge coal because the blast furnaces are normally minimum height is around 100 feet and they are fed, the raw materials are fed from the top. So, the feed material for raw material for a blast furnace is basically you need the hematitic ore Fe2O3 and I need to take out my oxygen. So, I need a reductant. So, I add coal, but for supply of C, then you get CO2 plus CO and like that you are basically trying to, and then whatever impurities are there with the iron and your coal, that has to be also separated, otherwise your effective volume of your furnace will be reduced. So, they have to be converted into a molten stage. So, normally the major impurities are silicates. So, we have to supply some source of calcium, magnesium like that, so that I make calcium silicate, magnesium silicate. So, that is why we also add limestone, dolomite, okay, for sources of or as a source of your calcium and magnesium to convert my impurities into slag. So, coming back to this point, that is why I have described it. Now, what it requires that when you are feeding it from the top of 100 feet height, if I take a say snapshot of that, so it happens like this, that is the distribution of the raw materials. If I take a snapshot, it is having a different layer, like this is your Fe2O3, that is your hematite. Then next layer, both the layers should be fluxes, that is your that is your fluxus, nothing but limestone and dolomite, and then it is basically the source of your carbon as a source of heat, as a source of reductant. So, there I need coke, not coal. Why? Because the gases, when you are heating, the reactions are that oxygen you are converting into CO2 and CO. So, this reaction goes on, one is endothermic, one is exothermic. So, you have to control that. So, you need the permeability of the gases, otherwise what will happen? The gases will not be able, whatever the coke, the carbon you have converted, it will not have access to this oxygen. So, it cannot be used as a reductant unless and until you have got proper flow of your gases through the bed. So, I need to maintain the bed permeability to a certain level. So, I cannot charge very fine particles there, because if I have very fine particles, my permeability of my bed will be very less. So, my gas flow will be inconsistent. So, my reduction kinetics will suffer. So, that is why there are size restrictions for all these materials, specifically for iron ore. That is what I said, they want minus 40 plus 10 mm particles. There is some compromise now, minus 30 plus 8 or something like that. Then for coke also, it is all fluxes are also of similar sizes, because what happens when I have bigger spherical particles, then you see that there are some holes, there are some bed porosities in between, but this pore sizes will be very less if I have very fine particles. Now, what will happen? Coal is by nature is very friable, that means it is very soft material. Now, if I am feeding it from a height of 100 feet, so that will be fragmented into very fine sizes. So, then all these porosities, permeable the pores, they will be just choked. So, your blast furnace operation will be very difficult to operate a blast furnace in that condition. So, I have to feed a coke. Now, what is coke? Now, that is a typical property associated with certain varieties of coal. That is, when you burn the coal in absence of oxygen, when you heat the coal in absence of oxygen, that is called a carbonization. Then the volatile matters will go out, that is the hydrocarbons. What will be remaining with, if that is having a lumpy mass, that is called a cake formation. So, that cake formation is there, and if it has got certain strength, there is some test, it is called caking index. Okay. So, there is some test, then if it passes through that and it gives you the confidence that okay, if I pour that material from the height of that, and the nature of degradation will not be much, and it will help maintaining that permeability of the bed, then only I can accept it. So, this variety of coal which is having this type of coking property, we call it metallurgical coal or coking coal. We have very limited resources of coking coal in our country. It is mostly concentrated in the Jharia coal field, but we do not have much problem with the reserves of thermal coal. Of course, with the quality we have got problem, but not with the quantity. But with coking coal we have got problem with both quality as well as quantity and availability. Okay. What happened to that? Okay. So, because of this, the coal quality means these are basically the different one, that is, one is caking index, that what is the strength of that coal once you have removed the volatile matter in absence of oxygen. That is a very, very important property. Then from a power plant uses, that is for your conversion of energy, the moisture content. Now, suppose you have seen that in the formation that you can have moisture, and this moisture could be of two different broad varieties. One is your inherent moisture. That means, as I am coming back to that example, suppose there is water and is all buried and they are basically decomposed. So, that water will be inside the matrix of my material. From outside it is very difficult to feel, to know that how much of water is there, but that water we cannot do anything. Okay? That is called the inherent moisture, and that goes out at around 560 degree centigrade temperature, that is called dehydroxylation temperature. But another temperature is that, that is for making my coal suitable for a power grid. After mining we use water as a medium fluid. So, we will have some surface moisture. Surface moisture, the nature could be the moisture adhered to the surfaces of the particles. The moisture could be coming because of the entrapment because of different particles. Like here, if I have different coals of different sizes, the moisture could be entrapped into that. So, you will have surface moistures. Now, imagine that your power plant is located around 500 kilometers from your mine site. Your coal what you are transporting, that is having 20% moisture. So, unnecessary you are burning your fuel only to transport water, that I have got no role to play. Plus, when I have water with this, my heat value goes down, because when I am trying to heat it up, because that also will consume more energy. So, more the amount of moisture, the quality degrades. So, that is the also moisture is also impurity in my coal. Then as again same thing, like say suppose if I have got your coal having 40% as, 40% as means roughly 42% suppose mineral matter. Now, if I am burning that coal, so I will be getting the energy out of this 58% material. So, 42% material I have unnecessarily transported it for 500 kilometers, 700 kilometers, I paid money on that, and then I have also used my energy for the conversion. In a power plant, how do you convert energy? That is, you generate steam, and then with that you run your turbines, isn't it? So, that is a basically deterrent for that steam generation, because you are not getting heat. So, unnecessarily you are consuming heat also. So, then your cost of production for energy also goes up, and then after that what you are left with, what you are going to do with that your ash forming materials, that becomes your waste material, that we call it fly ash or bottom ash. So, that becomes a problem. So, if in the mine site, if at the mine site if you can remove some of these ashes, that is what is the coal washing basically, and there is a compromise solution for that, because if I want to discard my ash, I may be discarding some kind of my carbon also. So, how do I do it and all that is the subject of coal washing. So, ash is also a very important material, important coal quality assessment one. Volatile matter, it does not give me much of heat value, because it just goes out immediately, but they are volatile substances. Like if I have tar with the coal, because I need for converting, say suppose 1 liter of water I want to convert it into steam, even if I have some 200 degree centigrade temperature, I will not get immediately the steam, I need some duration of that. But before that, if my volatile matter goes out, it does not help me anyway. So, that is also a deterrent in that case. Okay. Then fixed carbon, that means how much I am left with, that is if I subtract from 100, so suppose I have got 100 unit, then subtract it from that 100 moisture, ash and volatile matter, what I am left with, we say that that is approximately my carbon content of my coal. That carbon content, I may have more carbon in the volatile matter as a hydrocarbon, but that carbon is not basically being used for my heat generation. So, this is the fixed carbon which I am able to convert it for my energy generation, that is why I call it fixed carbon. Okay. Then sulfur, fortunately Indian coals we do not have much problem, but one gentleman has come from northeast. You know, in Assam coal we have got huge deposit of good quality coal in Assam, but there the main problem is with the sulfur. And the sulfur, if sulfur is there, what is the problem? First thing is that if you burn it, environment problems will be there. And say suppose that is a coking coal, if you pour it into blast furnace, the sulfur will degrade the quality of my steel and all this, because of your rolling and all these problems will be there. You cannot have sulfur. So, I have to remove that sulfur. That is also the problem with US coal, but the problem is that US coal, the most of the sulfur is coming from pyrite, that is a mineral FeS2, but our northeast region coal, the sulfur is mostly organic sulfur, and this organic sulfur are basically distributed along the matrix of my coal. So, it has to be ground to very fine sizes, which makes the entire process not economically viable at this moment. So, here there is a research problem for you, which I am not telling, it is there already, but I am just mentioning. So, there is a research problem for this if you can solve it. Okay. Then if I have mercury like your hazardous materials, it can cause pollution and all this. Very important property is that heating value. That is, how much is the heating value? Normally we express it by kilocalorie per kg. That is, if I burn 1 kg of coal, how much of energy I will get. So, there is a test called bomb calorimetry test, and you do it and you get to know what is the heating value of that coal. So, our coal pricing is basically based on that, we call it GCV, gross calorific value for thermal coal. How much is the heat value associated with that? Your pricing is basically based on that. Then from a washing point of view or from a characteristic point of view, even for coal quality, like for your transportation purposes, for various clients will have different size limitations. That is, what is the size, what is the specific gravity distributions, because I am buying the coal from you as a miner, because I have a plan that I have got a captive steel plant, and there I can have your coke making, but if that quality does not match, if that size and your density does not tell me that okay, it is washable or not, then why should I buy it, even if the caking index is good. So, the size and specific gravity is also very important quality, your say the indicators. Caking index we have already discussed. Ash melting temperature, that is very important one, we call it ash fusion temperature. Like say, suppose we are burning coal for converting your energy. Now, if your ash forming materials, they basically melt immediately. So, what will happen? So, they can adhere to the surfaces of my boiler tubes, and I can have your boiler tube failures because of choking or maybe because of corrosions and all this. Okay. So, the ash fusion temperature, ash melting temperature is also very important quality indicators. Now, coal utilization, I have said that for power and for coking for steel, even we can use for gasification. Many times we have got gases, and if I can take out those gases and I can use it like methane, mostly they are with the coal bed. Methane is a very big area of research these days, and in Munidi, in our say Dhanbad area, there is one project going on to mine this your say methane gas from there. Liquefaction in China, they are doing a lot of work on this. Even in our country in CFRI, that is now it is CIMFAR. What they wanted to do, that is in China they have developed this technology, many places the technology is not unknown. They are basically putting the fine coal and water into under high pressure, and they are converting into a some kind of your substitute for your furnace oil. So, I can use it as a fuel substitute, okay. But what will be the kinetics, what type of composition should be there, what is the petrographic compositions of that coal, what kind of technology we need, that is basically a challenge. Then for cement making as a building materials, we need that. Even many times you can get chemicals out of that, like when hydrocarbons, when it is going out, you can get the benzene from that, you can get many types of chemicals, if you know that how to separate them, how to isolate them, and you can convert it into chemicals, coal chemicals. So, coal is a very useful resource. Okay. Now, quality concerned by users. So, coal business, if you look at, it is basically coal price versus quality in different places and conditions. It varies from place to place, it depends on the requirement. Suppose today the our foreign countries, they say that we won't supply you coking coal. Then what will happen? Whatever coking coal we have, the price will go up. Okay. So, you don't have any control. So, it depends on, it is basically demand supply type of situations. Okay. Then steam coal, it is basically depends, and here also for coking coal also it depends that whether it is prime coking coal, whether it is semi coking coal, whether it is weekly coking coal. There are so many varieties for coking coal even. I am not getting into that detail for that. For steam coal, so moisture, ash, volatile, heating value, sulfur content, mercury, ash fusion, all together they tell you that what will be the pricing of that coal. One from energy availability, another is what type of environmental problem I am going to face after burning that coal. That depends on what type of impurities you have. So, not only the heat value is important, is what type of impurities I have, that also determines what will be the pricing for that. Coking and steel companies are basically they deal with the rank, that they want to know the maturity of the coal. That means indirectly I have some kind of your understanding of the nature of that coal, that how much of inherent moisture will be there, what type of your carbon content will be there. But then the moisture, as volatile matter, sulfur content, coking properties. For gasification and liquefaction purpose, they are more worried about moisture, sulfur and ash. Coal chemical industry need to know there is AL is missing, physical and chemical properties, coking properties, ash contents like that. Okay. So, what is coal preparation then? Now, coal preparation, I will start with this coal beneficiation. So, is the process of removal of the contaminants. So, what I have to do? First, I have to know that this coal I have to process for whom? Who is my client, and what are their specifications, what are their requirements. Then I have to know what are the contaminants in my coal, what are the materials I have to separate from that entire assemblage. Okay. Then we decide that what type of technique we will be using. So, and the lower grade coal to achieve a product quality which is suitable to the application of the end user. In short, I will say that mined coal, today whatever we are mining, whether it is coking or non-coking, does not matter, it is having average ash content varies from 40 to 50%. And the quality requirement for coking coal that is imposed by the metallurgists for steel plant, they say that we do not say to maintain that or not, that is a different issue, but their requirement is that in coal, my ash content should not be more than 17.5%. That is the textbook number. Okay. That is more than 17.5%. If it is more than that, so every 1% ash increases, my blast furnace productivity decreases by around 3%. So, basically they want 17.5 to 18% ash. For non-coking coal, for thermal coal, and there is a circular by the Ministry of Environment and Forest, that MOEF, that from an environment control point of view, that is, if your mine is located more than 1000 kilometer from a power plant, then you cannot transport coal having more than 34% ash. That is a general, and that is how the concept of non-coking coal beneficiation also has come slowly to the Indian market. Okay. But now Coal India or the major coal producers, they have understood, they have realized that even though we do not have any restriction below 1000 kilometer, if I within 1000 kilometer, then I am not governed by the restrictions, but still if I sell the upgraded coal having 34% ash, my return on investment is more, I get more value. So, because the lesser the ash, more the heat value and more the pricing of the coal. So, how do I remove my impurities? That is called the coal washing selectively. Why washing? Because we essentially use water. So, some people jokingly they say that it is like your washerman's job. कोयला धो रहे हो मतलब क्या, coal washing. It is not. There is some physics involved, there is science involved. We have to understand that. Okay. So, coal preparation is a broader term used to describe the complete process of sizing. That is, many times I may not need to wash the coal, upgrade the quality, but I need to conform to the quality related to size distribution. So, I need only to do sizing. So, when I am doing only sizing, that is breaking the coal by a crusher and controlling the size distribution, so that is also part of coal preparation. So, coal preparation is a broader term where coal washing is one part of that. So, coal preparation actually includes sizing, handling and washing of the run of mine coal. Okay. Run of mine means whatever you have got it from directly from the mine. Now, if you look at the mineral impurities in Indian coals, normally what you get, that is shell material, that is halite, montmorillonite, macovite, like that, it is around 5 to 10%, but you have got this type of clayey components, that is kaolin, and basically very frequent and dominant, it is around 60 to 85%. Normally you get that, and that is the problem with our Indian coal, that is these clays are basically very fine materials. So, for liberation size becomes very finer and finer. Okay. So, that is the, and they are intermixed with the matrix of my carbon and all that. That is the typical problem with our Indian coal. Then we can have sulphide, carbonates, oxides and other accessory minerals into my ash forming materials. So, here the challenge is coal is basically relatively not very high valued commodity as a raw material. It is not a very high value, like it is not gold or diamond. Okay. So, but our money involved is huge, because we need huge amount of coal to generate either say power or maybe to generate steel, to get the steel. We need huge quantities. So, when I am dealing with huge quantities, how do I separate them based on the simplest method, the physical property difference? The good thing about coal is that it is your carbon rich component, say actually part, the specific gravity of that is basically about 1.2, the specific gravity, it varies from 1.12 to 1.35, the specific gravity of the carbon rich part. Okay. And the specific gravity of impurities typically varies from 1.6 to 2.6. So, the good thing about coal, the formation is such that I can have two boundary conditions we can specify, which is not possible for minerals in most of the cases. Okay. That I know that the specific gravity varies from 1.2 to 2.6. and mostly I have to concentrate in between 1.4 to 1.8 or maybe to some extent up to 1.9 or maybe 2. Okay. So, here, so if I know the specific gravity, there is a specific gravity difference between my carbon rich part and mineral rich part, and then the same settling velocity differential principle I can apply to separate them. But how do I know what is the density of my particle? And that too millions of particles. I am not talking about a single particle, what is the density of a single particle. And I need to have this assessment very quickly, although it may not be accurate, but I need to have some assessment of the your distribution of the different density materials. So, for that there is a very simple test, we call it your sink float test, and that is called the entire test, the process called washability analysis. That is, whether the coal is washable by the conventional gravity concentration method or not, that we look at, that we conclude based on the data we generate based on that float sink test. Now, I will come back to this, but before that let me tell you what is that test. It is a very simple test. Now, when I know that my density varies from 1.2 to 2.6, and I know that 1.2, that pure coal, I am not interested, because I may get that, but my quantity of that coal will be very less. I need much more quantity. Okay. So, you can start with, you can have different buckets, okay, and starting from, and I can have liquids which can give me exactly the density I want. What are the liquids I can use? That is, one is your bromoform, where specific gravity is 2.89. Carbon tetrachloride is 1.59. Zinc chloride, that is 2.9, okay, that is a salt solution, but for liquids, and then this 2.89 and carbon tetrachloride 1.59, and I can take benzene, sometimes I may take kerosene. There are ways they can be dissolved into that, they can have a solution with that. Normally we take benzene, which is around 0.89, okay. So 0.89 and 1.59, I know stoichiometrically how much I have to mix. I can have a solution, because of that they are easily soluble in each other. So I can calculate it, and I can precisely maintain 1.2, 1.3, 1.4 up to 1.58. 1.58 I can go, because its specific gravity is 1.59. So if I need more than that, I will use bromoform. So, but the unfortunate thing is that these two are very costly material, and they are volatile. Other bad thing is that they are toxic, they are hazardous, okay, but still we use them. So when you use, if you use any case, any time, you use it in open atmosphere. Don't do it in a closed room, because you will be inhaling and all that, and please use mask for that. So, and then at different buckets I maintain different densities like 1.3, 1.4, 1.5, 1.6, whatever interval I want. If I need more precise, I can have 1.3, 1.35, 1.4, 1.45, like that intervals. Then what I do, now I have sampled, that is, the sampling is very essential. Suppose 5 kilograms of material, for which I want to know the density distributions, how they are distributed and what are their qualities, okay, to conclude that whether my coal is washable by the conventional washing techniques, not. Now what I can do, say suppose I have got the highest density is 1.8, that bucket. Now I pour that 5 kilograms material into that bucket slowly, and let it be there for 10 minutes. I will first stir it, and then I will allow it to settle on their own setting velocity, okay. 10 minutes, 15 minutes time you can give, there is standards for that. So that I am not going into detail. So what will happen? The particles which are heavier than 1.8, they will settle, isn't it? And lighter than that, that will be floated. So I can tell that these particles are heavier than 1.8, and I know the extreme condition is, extreme density is 2.6. So I can easily say that this particle density lies within 1.8 to 2.6, also specific gravity lies in that. Now the float fraction, whatever I have got, I can selectively collect it by using some kind of your chunni type of thing, you know, and then you transfer it to the next one, next bucket, which is having 1.7 density. Again you stir it and let it settle based on its density. So again something will, which are heavier than 1.7 but lighter than 1.8. Mind it, they are float fraction of 1.8 specific gravity. So that means they are lighter than 1.8, but as they have sunk at 1.7, I can say that that density is within 1.7 to 1.8, the specific gravity. That is how I am giving, I am basically discretizing the densities, okay. Like that I can go up to this 1.3, okay. Now what do we do? Now suppose I note down this data like this, that is, I say that below 1.3, that means the particles are lighter than 1.3 specific gravity. That means their density is in between 1.2 to 1.3, these particles. Okay. Now, out of the total population, that 5 kilograms, how much of that is being floated? I can calculate also that, because I can weigh them. So, suppose that is 29.1% of the total population. Okay. Like that for different one, that is 1.3 to 1.4, that means these particles are heavier than 1.3 but lighter than 1.4. So, how much is that? That is 5.5% like that, and then above 1.8, that is it is only 4.8. That means they are basically heavier than 1.8, that means they are in between 1.8 to 2.6. So, I have got the density range, I have discretized it. I also have the relative weightages. What are the relative weight percentages? Now, what we can do? Now, these samples, whatever we are getting, I can take the representative samples from them, and then I can do the ash analysis. Very simple one. You burn it at 825 degrees centigrade for 1 hour in oxidizing atmosphere. You take out, you see that how much of material is there. By weight loss method, you can get the ash percentages. Okay. So, because ash is basically one quality assessment parameter, more the ash is lesser the value. So, then I get to know, because it is 1.3 float. So, that means we are very close to the carbon rich part. So, naturally its ash content should be less, isn't it? And that also you can cross check that whether I have misplaced the tags, that is what happens normally. 1.3 tags has gone to 1.8 and 1.8 tags have come to 1.3 and you are confused. So, if you see that 1.3 float is 64% ash, there is some problem, you have to repeat it. Okay? It cannot, because we are going closer to the carbon rich part. So, it is 6.4%, and then that is how we are getting the distribution of my ashes. So, what we have done? So, basically we have got a density distributions, and along with that quality distributions. Okay. Now, what we can do? That is, now steel plant people, suppose this is a coking coal. Now, steel plant they need 18% ash. Okay. So, what we can do? That is, if I want 18% ash, how much of material will be sellable? Suppose I start with 100 tons of material. Now, my steel plant is saying that there is some cost parameter associated with it. Now, suppose 100 tons of material, if I sell it as it is, I will sell it to power plant. I am not going to sell it to metallurgical plant, although it is a coking coal. Okay. Now, say suppose I am getting a return of 100 into say suppose 8,000 rupees per ton. So, that is basically I am getting the money paid back by selling this, the mined product. But say suppose out of this 100 tons, if I upgrade it to a quality where I can sell 60 tons of material which is having a value of 60 into say suppose 15,000 rupees per ton, because the quality has been upgraded, and the remaining 40, of course, this quality will be inferior than this initial 100 ton, because I have upgraded it, a simple mass balance. So, I will have 40 and say suppose this is 4,000. So, I have to add up this together. So, that will be your 90 into this 1000 plus 160 plus. So, I have to add that, and I have to see that whether this is more or this is more, and in between you have to add the cost of washing, the capital investment, environmental norms, and all this you have to look at. So, in totality if you find that it is giving me more dollars or more rupees, then yes, I will set up a washery, otherwise I will not. So, how much I will get, that is very important here, because the economics lies whether I get 60 tons of that quality 18% or 6 tons. If it is 6 tons, it will be simply 6 into 15,000. So, remaining will come into that 94. So, how do I know? So, for that what I can do, that is I can do a cumulative weight percent. What cumulative weight percent means? That means suppose if I did not have this 1.5 bucket, so suppose I start with a bucket, I start with a bucket of only 1.6, then what will happen? The material which floated at 1.4 and 1.5, that will also float into 1.6. So, how much? That will be a cumulative effect of that. How much will be in the sink? Say suppose I have got only 1.6. So, whichever has sunk into 1.6, that will also be whatever it has sunk into 1.7 and 1.8, that will also will be in the sink fraction of 1.6. So, that is why we need to do that what is the cumulative weight percent. So, for this below 1.3, how much will be floated? It is only the one estimate, it is the same value 29.1. But if I start with 1.4, this will be this plus this, that is 34.6%. Like that I can add them together, and ultimately when you go to the 2.6, how much will be floated? Everything should be floated. So, above 1 means 1.8 means suppose you are 2.6. So, you will be having 100%. And what will be the quality of this product? So, suppose I start with 1.6, whatever is floated, what will be the quality of that? How much will be the ash content of that? That is a little bit tricky, and we will have tutorials, and definitely in the exam I will ask questions on this. Okay. So, whoever has registered for credit must understand this. So, here say the quality will be same 6.4, but next one you see the here it is 16.1, but I have written 7.9. Why? Now, the ash content here will be 29.1 multiplied by 6.4 plus 5.5 into 16.1 divided by 29.1 plus 5.5. That will be the ash content of that 7.9. So, when you are getting this 26.3, it is nothing but the ash content of my feed coal, that is the original population of 100 tons, that is giving me. Okay. So, what is my starting ash? 26.3, that is giving me. Now, at 18%, now it is very easy. Now, if I plot this your specific gravity versus this float ash fraction or maybe cumulative weight percent. So, see suppose we assume that this is 18%, how much of material I will be getting? 73.4%. At what conditions I have to separate them? In between 1.5 to 1.6 specific gravity. So, these type of informations we generate by plotting series of curves out of that, but I leave it to Professor Sumantra Bhattacharya to discuss about that, because he loves to discuss that. So, he will be coming on 16th afternoon, he will be talking about that. Okay. I leave it to him, but this is the essence, this is the basically you get to know, but here what I have not mentioned, that is very important, that what is the starting size of this coal, what size we are talking. Okay. We have discussed only about the density distribution and basically the quality distributions, but at what size? Can I do it with the raw material ROM coal, the mined coal? That we have to decide. And so, suppose even your mined coal, if it gives you the proper liberation, but for the separation do you have equipment? Say suppose I have to process in my equipment a 1 meter size of coal, whether my existing equipment can handle a feed size of 1 meter, that also I have to look at. So, this is basically a combination of everything, you have to make a judgment whether I will be using that, what are the availabilities and all that. So, normally if you look at the Indian coals, it is a generic one. For coking coal the problem is more, because I need to reduce the ash content by from a 45 to 18%. For coking, for non-coking coal it is up to 34. The challenge is less, but there the money you can spend on coking coal is more, because you have got more value onto this. So, normally we have seen that 50 to 13 mm. So, what do we do? Normally we group them into different sizes. We say this is the coarse coal fraction, this is the medium coal fraction, this is the fine coal. Fine coal means it is minus 0.5, and you see that process is different. Now we are not talking about gravity concentration, now we are talking about surface modifiers, the froth fluoridation is chemistry based processes we are coming. That is why we call it fine, because it is up to me, the definition is that more the difficulty you face in processing, you put those adjectives that whether it is fine or ultra fine and all this. If tomorrow, if you can design a good gravity concentration technique to process, we may not call it fine. We may say that, okay, this is quite common to process that also. Today we are saying it is a fine because we are facing difficulties. Okay. So, basically the equipment sizing and the techniques what we use, that is also basically dependent on feed sizes, what type of feeds you have, because it is evident from this size that more the size, the coarser is the size, it is very easy to separate because your mass is more. So, mass is more means, say suppose your difference in the relative settling velocity is more. So, when I have relative positional difference easily achieved, I can separate them easily. So, for coarse coal, the problem is less because the individual masses are more. So, what I am saying, say suppose a 40 mm coal having two particles, two density classes like your 1.5 and 1.7. So, if I put it into a water, the settling velocity difference will be huge. We can calculate that because the size basically controls also the mass of that particle. But when the size is basically going to the finer range, my mass is getting lesser. So, I face more difficulty in separating them into a fluid medium because their settling velocity difference is less. So, I need to impose other forces like centrifugal forces, fluidization theories, like other techniques we have to impose to separate that. That is why you look at that this coal, when it is coarse, we use jigs or heavy media bursts, normal G forces, normal gravitational force field. When it is 13 to 0.5 mm, dense medium cyclones, then minus 0.5 generally froth flotation. So, size matters, size is very, very important, and I need to do that Floatzing test what I have discussed. I must mention that what is the size of the coal, okay? And that is how we decide that whether the coal is washable at what sizes. So, here the mass balances are, suppose what I have to do to decide that whether I will set up a washery or not. Suppose I have got 100 tons, again I am coming back to that number 100 tons. When I am saying minus 50 plus 13, how much is that I will get, minus 50 plus 13? Again that depends on my control in my comminution circuit, your crusher screening circuit. Okay. Suppose I get only 20% or say suppose I get 2% of that. Do I need to have a circuit specifically designed for 2% of coal? No, that is absolutely not required. But if it is 30%, 40%, so you have to make the decisions that what is the critical content, okay, that is the engineering challenges. Okay. So, I need to know that how much of minus 50 plus 13 I will be having, and that is also dictated by the nature of the coal, that is your friability, that relative hardnesses, okay. What type of crushing equipment you have used. So, what is the comminution equipment I have used, that is also basically deciding factor that how do I control these sizes, the quantity of that. So, then minus 13 plus 0.5 how much I will be getting. So, when I am getting reasonable amount of this, then we will say okay, we will separate them first based on sizes, and then we will have different equipment for different circuits, we will be separating them for upgradation, and then at the end again we will mix them up and we will sell it to Steel Authority of India Limited. Okay. Now, again I am coming to that jigging, I have discussed this is basically a fluidization and defluidization techniques, and you can have your sinusoidal motion like this, but present days the people are basically researching, there are some jigs, what they are saying that do I need the pulsion and suction of the same amplitude, it may not be required. So, I can reduce this cycle so that I can reduce the residence time of my particles, that is the type of research you are doing, that is already in operation. Okay. Some jigs are there That is basically the mechanical engineers are working on that, wave generations and all this. Okay. How do I do it? Complex fluid mechanics here. Chemical engineers also can control. There is another type of equipment which I have not discussed in the first session, that is called a dense medium bath. It is nothing but like a huge container, and say suppose I am pouring coal into that, I have got a medium suspension, I have increased the density of my I am having some suspensions like your float and sink. I can create that environment by suspending some materials, because I cannot use your bromoform or carbon tetrachloride. One is economically not viable, toxic, costly. So, I can have a substitute, like if I have very fine particles, because I will be using minus 50 plus 13 mm coal. So, if I have very fine magnetite particles suppose, and if I keep them in suspension by some means, by creating some turbulence into that, and they are in suspension. So, I am increasing the relative density of my slurry, and then I can maintain that 1.5 density, and I can have a float sink effect. That is the technique called dense medium bath. For minerals also we use, but here the challenge is basically the typical design changes are there in case of coal processing equipment and in case of mineral processing equipment. Please try to understand that in coal I am having around 40 to 50% ash. So, it is almost distributed 50-50, wanted and unwanted. For mineral I said 2.5 ppm gold, that is my wanted material. So, my unwanted material is basically coming in and going out. So, the type of design I will have for the product discharge, the volume to be handled per unit time is different. So, that makes the changes in the design and all this. Okay? That is the fundamental difference between your coal processing equipment, but fundamentals remain same, but the design aspects are different, the material handling systems. Then we have got dense medium cyclones. We will talk more about this in subsequent lectures, but to introduce you, that is what we do, we have got a cylindro-conical body, it is called a cyclonic separator also, but sorry. In case of coal, when we use, we try to use it as a density separator than a size separator. Okay. How do I do it? Now, feed in terms of your coal, water mixture, and we also mix some fine magnetite particles. What that fineness is normally below 40 micron, and the coal what we are sending, it is 13 below 13 mm to minus 13 to 0.5. Minus means it is finer than 13 mm, plus means coarser than 0.5 mm. So, coal is much coarser than my magnetite particle. Although my magnetite specific gravity is more than my coal, magnetite specific gravity is 5.15, my coal highest specific gravity is 2.6, that is the cell rich part. But because the size is very small, so their settling velocity is much less than my coal particles. Okay. So, I feed it at a very high pressure tangentially. So, there is a swirling motion created. Okay. When the swirling motion created, and you see that there is a cylindro-conical section is there. So, this one is called the included angle, and this discharge, there are two discharge end, one is called overflow or we call it vortex finder, this is called underflow or we call it spigot. Okay. Now, we try to imagine that what will happen to a particle, that when I am injecting it at a very high pressure and there is a tangential entry. So, there is a swirling motion and particle experiencing two opposite forces. One is centrifugal force, which is trying to pull it towards the wall, and another one is drag force, which is trying to pull it towards the axis in a radial direction. And gravitational force field is very weak in relation to these two forces. So, we can ignore that. So, there is a relative competition between these two forces. Now, it depends on what is the mass of this particle, it is mv square by r. So, when my particle m stands for mass, v stands for velocity, r stands for the radius of orbit. Okay. What is the orbit of rotation? Okay. So, when my m is more, it may be more because of the size, because of the density, but we have fed minus 13 plus 0.5 huge size range. So, I cannot control that. Now, what is happening? Now, the bigger mass particle will be thrown towards the wall, they will hit the wall radially and they will lose the radial momentum, and then because of gravity now they will come down and they will go out of the system through the underflow. Relatively finer particles, this is much more complex than this, we will discuss more on this. We may be having 6-7 hours lecture on this fluid mechanics of this separator, I am just trying to introduce. So, the relatively finer particles, they will be close to this axis. Now, you see what will happen, there is a cylinder conical geometry, because of that there is a pressure gradient, there is a pressure drop from here to here, because pressure is nothing but force per unit area, and your force is R is changing, R is bigger in the cylindrical portion. So, the particle experiencing the centrifugal force is much less than when it is coming to the conical portion, because of the R is less. Okay. So, force is more here and your cross section area is less. So, there is a huge pressure drop from this region to this region, okay, and this is open to the atmosphere. So, because of this pressure drop, air automatically gets sucked from the atmosphere to bring it to the equilibrium, that is called the inner vortex. So, there is the outer vortex because of your tangential entry, and because of the pressure drop, air basically comes in and it tries to go out of the system through the overflow. I give this analogy, still it is not being understood, that is what we are researching, that is how the particles are being transported inside a cyclone. Even in literature is silent about that. Okay. So, I give this analogy, that is how the fine particles which are basically very close to this axial region, what is the mechanism of transport of that? The analogy is that, say, suppose you are standing in a platform where your Rajdhani Express or Shatabdi Express does not have a stop, it is a through train and it goes at a speed of, say, suppose 140 kilometers per hour. You have probably noticed that there is some yellow line, and that is an announcement that stay away from the yellow line, you know, because what will happen, even though I do not have a direct contact, suppose I am here and Rajdhani is going at 140 kilometer speed. So, the local drag will be created, and there you are just like a particle and you will be also dragged, you will be transported with that. How far you will be transported, that depends. Okay. Maybe you will become nano size within a few seconds. Okay. So, that is a different thing. So, that is how probably these finer particles, they are getting transported through this along with this air core, and some water also getting transported. That is how you separate fine and ultra fine particles, but that is for classification. But for coal, I need to separate based on density. So, what I am doing, I have introduced magnetite, and this magnetite basically, because of the fineness of that, they remain in suspension, because their residence time inside the vessel is more than my coal particles, because of the mass is less. So, I am having artificial increase in my suspension density, so that I can negate the size effect and I can have a float sink effect. And the float material, they are being transported by the air core to this. So, that means I will get a clean coal through the overflow, and I will have cell material, that is unwanted material, coming through the underflow. That is how we separate it in a dense medium cyclone. Why we call it dense medium? Because we are injecting artificial a medium to artificially increase my suspension density. Why magnetite we are using? First thing is that it is abundant, it is easily available, it is cheap, and good thing about magnetite is that I have to recover this magnetite from overflow and underflow, they will be coming also. So, I can put it into a magnetic field and I can just basically separate magnetic and non-magnetic, there are magnetic separators we can use. So, I can regenerate, I can reuse it, okay. That is why we use it, the magnetite. There are many other reasons also. Flotation systems we have already discussed. So, we can have different series of basically flotation cells. These days people are suggesting that you can combine them and you can have a column flotation, but the capacity is an issue. I said in the morning also. Now, that is the technical aspect of coal washing for introduction part. If you look at this data may be wrong also, I have taken it from the Ministry of Coal sites. Okay. So, this is the existing coal washeries of CSI to CIL. You see in 1969 also we had an washery, 50 years, almost 50 years back, we are washing this. And then we have got so many coal washeries now, we have got the non-coking coal washeries too. And now the thing is that here, in coal washing, I can see, I can tell you that there will be a lot of opportunity, job opportunity, business opportunity, because Coal India has decided that by 2020 they will be going for 1 billion ton of coal production. Today it is around 530, 540 million ton. So they want to double their production, and they have also decided that they are going to sell washed coal. So that means you can think of how many new washeries will be coming up, and it is not only that you have to work in washery, who will be supplying the equipment, who will be supplying the technology, the software engineers, your simulation packages, all sorts of. So you can get into software technology related to your engineering discipline. Okay, it is not necessary that you have to go for your other industries. You can stick to your industry, but you can be in the software. Then washing processes, if you look, if I summarize, you see that basically dense medium cyclones, we call it sometimes heavy media cyclone, flotation, desaling jig, heavy media bath, jig, flotation, jig, bath, and not many variations are there. That is what I want to highlight, that even though it is a very old process, the coal washing is mostly, I think it is more than 120 years old thing, but still you do not see that not many unit operations are there. It is either jig or dense medium cyclone, or maybe some kind of your heavy medium bath or some spirals. It is the same thing, we are giving only changing minor design changes. So you can come up with your bright ideas of removing the impurities, you can have fresh ideas, and you can get into the research domain also. That is, these technologies are basically very old technologies, but we do not have any alternative technologies. So there is enough opportunity for developing alternative technologies. Okay. And if you look at a typical flow sheet, that is what we call it a flow sheet. It looks ugly, but how do I read it, a flow sheet? Because then only you will understand that in a mineral processing also, when you go and visit, you will be having showing the flow sheets, but I advise that you look at it like this, you segment it, that what are the pre-treatment stages you have. You can have even the crushing, grinding stages also, the combination stages. So pre-treatment, you see that there are basically different sizes. You have got disliming screen. What disliming screen means? If I have clay materials, ultra fine materials, below 150 micron, below 45 micron particles, then what will happen? Because I am using a fluid medium, so that will change my viscosity, that will create viscosity related problem, my slurry rheology will be different. So I know that is a nuisance, why do not we take it out from the system before I put it into water? So my first step should be, that is how do I take it out if I have more slime contents, that is ultra fine particles. For that you need a process. So what process? That will be dictated by what type of particles, how much is there. So there could be disliming screen, there could be disliming cyclones, separator, classifier, what we have discussed. There could be screens, some kind of your disliming screens also. So whether I will select this or that, that depends on the character, based on the characteristic of my material and my basic knowledge of your each unit operations, and the capacity also. Then your main washing upgradation units, that is I can group them, that is cleaning unit. What is the primary dense medium cyclones, secondary dense medium cyclones? That means I am having two stages. That is in one go I cannot do it from 45 to 18%. Why don't you do it in stages? Okay. So that is nothing but the same process, but the scale of operation could be different, operating conditions could be different. Then for other sizes I will be having spirals, spiral concentrators, then you see the flotation cells for very fine sizes. That is how we should read vertically, segment it. Then it is subsequent treatment stages, that is when I have used this, I have to recover my magnetite, I have to recover my water, and then I have to have my product handling systems. Okay. So that is basically the drain and rinse screens, that is for dewatering segments. There is a thickening cyclones, belt filters and all this, that is basically dewatering units are there. Then your material handling, product handling, that is where the reject is going, for what purposes. So this coal I am sending it to metallurgical plant, I will get more value out of this. this one, that is your power plant coal, that is your thermal coal. So, I need to segregate it, and I need to have a different destination. So, I need to have different dispatch sections, and then there is a reject. What are the rejects? That is what I am going to do with that. If I am planning to dump it, where do I dump? What are the restrictions? What are the basically the leachable materials are there, whether it will contaminate the groundwater or not, that I have to look at. Then I have to have some kind of your impervious layer to be formed in the bottom. Then that is how basically you formulate, you look at your flow sheet, and this is where what I try to mention, that how do I link this. I have shown with the arrow, but these arrows are nothing but most of the cases either pipelines or maybe your belt conveyors or different conveying systems. So, and then when it is coming from this height to this height, so there we are using your gravity of course, but you need pumps, booster pumps you require. So, you need to have thorough knowledge on your pumps, pipeline system, slurry transportation system, bulk material handling system. Then there will be corrosion problem, there will be erosion problem. So, I need to have the detailed knowledge about material characteristics, material and your mind process material interactions. What will be the material, how do I control? There is all small numbers, there are numbers, is 110 tons per hour, this is 80 tons per hour. Now, every equipment is sensitive that to the how much of tonnages you are feeding, how do I control that? So, you need to have measuring systems. How do I measure that whether it is 110 tons per hour or not? How do I measure 110 tons per hour? So, we need mass flow meter. What is the calibration? How does it work? How do I do it? So, you need instrumentation, you need sensors, you need simulation packages to develop this type of your basically circuits. If I say that why you are using this, why you are not using some other thing, then you have to have the answers for you that this is the best for this type of scenario. So, that is where your optimization is coming, modeling, simulation and everything is coming, and essentially you see all this you are dealing with fluid. So, very basic knowledge I should have in the fluid mechanics, and it is all engineering discipline people, they can work together, then only we can develop the technologies. Otherwise, we have to bear what we have and we have to compromise. So, that is what I wanted to talk about this introduction to coal preparation. Thank you very much.